Assalamu alaikum dear students. In today's lecture we are going to start a new chapter, which is chapter number 6, and this is about counting. So in this video we are going to cover section 6.1 and 6.2. So let's start. Summary of these two sections is the first section covers the basics of counting, like addition rule, subtraction rule, multiplication rule, division rule, etc. And then 6.2 is about pigeonhole principle. So first section 6.1, which is about basics of counting. So section summary, we are going to learn product rule, sum rule, subtraction rule, division rule, and there are a few examples. And then there is tree diagram. This is also a way of counting. So first, product rule. The product rule is a procedure that can be broken down into a sequence of two tasks. There are n1 ways to do the first task and n2 ways to do the second task. Then there are n1 multiplied by n2 ways to do the procedure. For example, how many bit strings of length 7 are there? Since each of the 7 bits is either 0 or a 1. So we have two choices for every bit, right? So for every bit we have two choices. So the total number of choices is 2 multiplied by 2 multiplied by 2 multiplied by 7 times. So 2 to the power 7, that is 128. So this is the use of product rule in counting. Again, an example of product rule: how many different license plates can be made if each plate contains a sequence of 3 uppercase English letters followed by 3 digits. So we have 6 spaces to fill. First 3 spaces must be filled by the letters, and we have 26 choices for these 3 spaces, for each of these 3 spaces. And next is the condition that the next 3 spaces must be filled by the digits, and we have 10 choices for each of this space. So 26 multiplied by 26 multiplied by 26 multiplied by 10 multiplied by 10 multiplied by 10 are the total number of ways. So to make license plates, distinct license plates. So these are this much ways. Counting functions: how many functions are there from a set with m elements to a set with n elements? And since function represents a choice of one of the n elements, the codomain for each of the m elements in the domain. So the product rule tells us that there are n to the power m such functions. Okay, so n multiplied by n multiplied by n, m times will multiply n. Next example is counting one-to-one functions. How many one-to-one functions are there from a set with m elements to one with n elements? So we have the domain elements. Let's assume that the domain elements a1 a2 am. There are n ways to choose the values of a1 and n minus ways to choose the values for a2, since the function is one to one. So the product rule tells us that there are n into n minus 1, n minus 2 up till n minus m plus 1 such functions. Now telephone number plan. The North American number plan specifies that a telephone number consists of 10 digits. Okay, so consists of 10 digits consisting of 3-digit area code, a 3-digit office code, and 4-digit station code. Okay, so there are some restrictions on the digits. Let x denote a digit from 0 to 9. So wherever you find x, actually it will be a digit from 0 to 9, and the n denotes the digit from 2 to 9. Y denotes a digit from of 0 or 1. In the old plan, the format was NYX, that is area code is NYX, and then next code, 3-digit office code is NNX, and the station code, 4-digit station code is XX. So in a new plan, the format is NXX, NXX, and tetrax. So how many different telephone numbers are possible under the old plan and the new plan? So we'll use the product rule. So NYX first, we see that in how many ways NYX can be determined. So N, we have 8 choices in order to fill this in, and we have 2 choices for Y, and for X we have 10 choices, 0 to 9, that is we have 10 choices. So the area code can be made in 160 ways. So we have 160 area codes of this format. Okay, so NXX, so next format is for area code is NXX. So N can be chosen into in 8 ways. So X can be chosen in 10 ways. So we have 800 area code of this format. Now NNX format we have 640 office codes of this format. Similarly, N and the last part is 4-digit station code, and it can be, the number of ways can be determined by 10 multiplied by 10 multiplied by 10 multiplied by 10, because it consists of all x's, and x can be chosen in 10 ways. So we have 10 to the power 4, that is 10,000 ways. So the new plan old plan, NYX, NNX, XX, we have this much possible telephone numbers, and according to new plan we have this much telephone numbers. So we just multiply all these values we have derived. Next, counting a subset of a finite set, use the product rule to show that the number of different subsets of a finite set is 2 to the power order of S, that is number of elements in S. So when the elements of S are listed in an arbitrary order, there is one-to-one correspondence between subsets of S and the bit strings of length S. Okay, when the ith element is in the subset and the bit string has 1 in the ith position and 0 otherwise, so by the product rule, we have a total number of subsets is 2 to the power order of S. Now product rule in terms of sets can be written in this way. If we have M sets A1, A2, AM, then the number of ways for choosing an element from a Cartesian product A1 across A2 across A2 is done by choosing an element of A1 and multiplied by an element of A2, and then so on element number of elements in AM. So this is the rule written in set form. So similarly, you can read the examples. These examples are given in the book DNA Genomes. Next is the sum. So if a task can be done either in one of n ways or in one of n2 ways, so then the task can be done in n plus 1, n1 plus n2 ways. For example, the mathematics department must choose either a student or a faculty member as a representative of a university committee. How many choices are there for this representative? There are 37 members of mathematics faculty and 83 mathematics major, and no one is both a faculty member and a student. So total number of ways to choose a representative is 37 plus 83, which is 120 in total. So the sum rule in terms of sets, A union B, this OR actually represents union. A union B, order of A union B is order of A plus order of B. Or if we have M sets, then A1 union A2 union AM is equal to A1 order of A1 plus order of A2 up to order of AM. And now keep this in mind that A, B are disjoint, so there is no common factor in between A and B. Similarly, if we have more than two sets, then the sets are pairwise disjoint. So AI intersection AJ is phi whenever I is not equal to J. So we will study the case where there is something common between the sets, and this is called subtraction rule. And now example for sum and product rule. Suppose statement labels in a programming language can be either a single letter or a letter followed by a digit. Okay, so when we choose a single letter, there are how many ways? 26. Or this or actually represents addition. A letter followed by a digit. So a letter followed by a digit, number of ways can be found by using product rule. So let's see. So 26 for single letter plus this represents this or, and letter followed by a digit. So 26 letter and 10 digits, so 26 multiplied by 10 ways. So add them both, we have 26 total number of labels. Similarly, there are counting password problems. You can read it and let me know if there is some problem. Internet addresses, there is another example. Next is subtraction rule. This is also called principle of inclusion and exclusion. And in this case, if a task can be done either in one of n ways or in one of n2 ways, and then the total number of ways to do the task is n plus 1, n1 plus n2 minus the number of ways to do the task that are common to the two different ways. So in terms of sets, we can write it A union B minus is equal to order of A union B is equal to order of A plus order of B minus order of A intersection B. So when A intersection B was phi in sum rule, so actually there was 0 at this place. So this is also called the principle of inclusion-exclusion. This is important in the case. It has several applications in counting. So first example, counting bit string. How many bit strings of length? 8 either start with 1 bit or end with 2 bits, 00, 2 00 bits, right? So we have to form bit strings of length 8, right? If first place is fixed, that is it starts from 1, then there are 7 places, and we have 2 choices for each place, so 2 to the power 7. Total ways are 128. Now if last 2 are fixed, so we have 6 choices, and we have 2 choices for every space, so 2 to the power 6 ways. And but there is a possibility of overlapping of one type in the other type. Like if we are choosing bit string starting from 1, there is a possibility of ending the string with 00. So in case we are ending with 00, there are it consists of all the bit strings starting from 1 as well. So in order to minus this possibility, so let's see how many bit strings with one starting from 1 and ending at 00. So when first now 3 places are fixed, so we have 5 places, and for every place we have 2 choices, so total number of ways are 2 to the power 5, that is 32. So the total number of bit strings 128 plus 64 minus common number of ways, which is equal to 160. So this is the example of inclusion-exclusion principle. Next is called division rule. And division rule, if there are n by d ways to do a task, if it can be done using a procedure that can be carried out in n ways, Okay. Initially, we have n by d ways to do a task, and if we use a procedure that can be carried out in n ways, and for every way w, exactly d of the n ways correspond to way w. So let's have an example. I think it will be more uh, clear by with the help of example. So let's demonstrate this rule in this example, and let's see how does it work. So how many ways are there to seat 4 people around a circular table, where 2 seatings are considered the same when each person has the same left and right neighbor? So first of all, number the seats around the table from 1 to 4 clockwise. Okay, so there are 4 ways to select the person for the seat 1, 3 ways for seat 2, and then 2 ways for seat 3, and 1 way for seat 4. So they are total number of ways are 4 factorial, that is 24 to order the 4 people. But since 2 seatings are the same when each person has the same right and left neighbor, so for every choice for seat 1 we have the same seating. So therefore, by division rule, total different and distinct seating arrangements are 24 divided by 4. So we will divide by 4 because there are uh, 4 ways which are same because of right and left neighbor. Now there is another way of counting which is called tree diagram, and this is illustrated with the help of this example. An example is, suppose that I love discrete mathematics t-shirt, that is a t-shirt written I love discrete mathematics on, come in 5 different sizes. Okay, we have a t-shirt, so we'll start with 1 dot from where we'll draw the branches. So we have a t-shirt which comes in different sizes: small, medium, large, extra large, double XL. Each size comes in 4 colors. So white, green, red and black. So white, red, green, black. Medium white, red, green, black. Large white, red, green, black. White, red, green. So total numbers, just count the last oh yes, there is another. That is what, yeah, large, white, red, green, black, and XL, except XL, which comes only in red, green, and black. So it comes in 3 colors, and double XL, which comes only in green and black. Okay. Now the total number. So what is the minimum number of stores that the campus book store needs to stock to have one of each size and color available? So using this tree diagram, just count the uh, end nodes, and we have 1, 2, 3, 4, 8, 12, 13, 14, 15, 16, 17. So we have 17. The store must stock 17 t-shirts in order to have every size and every color. Now, exercise question. Question number 1. There are 18 mathematics majors and 325 computer science majors at a college. In how many ways can 2 representatives be picked so that one is mathematics major and other is a computer science major? So we'll use product rule. Mathematics major can be chosen in 18 ways. Computer science major can be chosen in 325 ways. So total number of ways to choose a representative is 18 multiplied by 325. The 2 representatives is 18 multiplied by 325, which is 5 at 50 ways. And in how many ways can one representative be picked who is either mathematics major or a computer science major? So this is the sum rule. 18 plus 325, that is 34 ways. Question number 21. How many positive integers between 50 and 100? and which are divisible by 7, and write the integers as well, which are divisible by 7 and which lie between 50 and 100. So they are 100 over 7 floor function, that is 14 integers less than 100 that are divisible by 7. Okay, and 50 over 7 floor function, that is equal to 7 of them are less than 50. So between 50 and 100 are 14 minus 7, right? So this is a subtraction rule or inclusion exclusion rule. And next, and these numbers are 56, 63, 70, 77, 84, 91 and 98. Now the divisible by 11, which integers are these? So we have floor function 10 over 100 over 11. This is the number of integers less than 100 which are divisible by 11. So minus number of integers less than 50 which are divisible by 11. So this is 9, this is 4, answer is 5, and these numbers are 55, 66, 77, 88 and 99. Similarly, you can do the part C on your own. Try it yourself and let me know if there is a problem. Okay, next, pigeonhole principle, section 6.2. Okay, in this section we are going to discuss pigeonhole principle and its generalized form. Pigeonhole principle actually works on the idea: if a flock of 20 pigeons roosts in a set of 19 pigeonholes, one of the pigeonhole must have more than one pigeon. Okay, so we have 19 pigeons to accommodate 19 pigeonholes to accommodate 20 pigeons, right? So there must be at least one pigeon hole in which more than one pigeons are staying, right? So this leads us to the lead us to form the pigeonhole principle of mathematics for counting. And if k is positive integer and k plus 1 objects are placed into k boxes, then at least one box contains 2 or more objects. Okay, it makes sense. So the pigeonhole principle, a function in terms of function, it's corollary. A function f from a set with k plus 1 elements to a set with k elements is not one-to-one, right? Pigeonhole principle, the use of pigeonhole principle. So let's understand this principle with the help of example. So in this example, among any group of 367 people, if there is a group of 367 people, right? So there must be at least 2 with the same birthday, because there are only 366 possible different birthdays. The generalized pigeonhole theorem, the generalized pigeonhole principle: if n objects are placed into k boxes, n objects are placed into k boxes, then there is at least one box containing n over k ceiling function objects, right? For example, among 100 people, there are at least ceiling function 100 over 12, that is 9, who were born in the same month. Because we have 12 months, right? So people are 100. So first 12 can be from different months, then second 12 again can be of different months. So we have 2 of each month, then again next 12, again next 12. So there is a possibility of 9 persons who were born in same month. Next example: how many cards must be selected from a standard deck of 52 cards to guarantee that at least 3 cards of same suit are chosen? Now, how many suits are there? There are 4 suits of cards, that is a spade, heart, club and diamond, right? So if we need to choose uh, 3 cards from same suit, right? So how many cards must be there in order to make sure that 3 cards from same suits are there? So we assume 4 boxes, one for each unit, each suit. Using generalized Pigeonhole theorem, at least one box contains n by 4 ceiling function cards. So we have to find n such that this condition holds. So at least 3 cards of one suit are selected if n by 4 ceiling function is greater or equal to 3. So the smallest integer n such that n by 4 is greater or equal to 3 is 2 into 4 plus 1, because when n is 8, then we have answer of the ceiling function is equal to 2. So this is greater than 2, that greater or equal to 3 if this n over 4 is greater than 2, right? So in order to make it greater than 2, n must be greater than 8, right? So n must be greater than 8, that is n can be 9. So the immediate integer which is greater than 8 is 9. So n is 9. So the answer of this question, that is, we have to choose 9 cards to make sure that 3 cards of the same suits are chosen. Okay. Part B. How many cards must be selected to guarantee that at least 3 hearts are selected? How many cards must be selected to guarantee that at least 3 hearts are selected? Okay. Now a deck contains 13 hearts and 39 cards which are not hearts. So while choosing the cards, initially we can have these 39 cards which are not hearts. So in order to make sure or in order to guarantee that at least 3 hearts are selected, we have to choose 42 cards, 39 which are not hearts plus 3 which are hearts. So it will make sure that at least 3 hearts are there. So a deck contains 13 hearts and 39 cards which are not hearts. So if we select 41 cards, we may have 39 cards which are not heart along with 2 hearts. So but if we choose 42 cards, so we must have at least 3 hearts. And this argument is not generalized form of Pigeonhole, but this is another way of counting. So that's all for today. Thank you so much.